Hi everyone. Today we shall discuss generalized heat conduction equation in cylindrical coordinates. So after this session you will be able to perceive the heat conduction equation in cylindrical coordinates and what do you mean by thermal diffusivity. So in the last session we shall discuss we discussed about heat conduction equation in Cartesian coordinate system. So now we shall go with cylindrical. In the earlier class I mentioned Cartesian means which has looks like a rectangle or a cube, so which is having three coordinates x, y, z and axis. Whereas in cylindrical coordinates, where cylinder is having the main criteria of radius, so that is one of the quadrant, and the other quadrant is z is a z axis, and the third quadrant is called as phi, which cuts with an angle of phi with respect to radius. So if you take this entire cylinder, if I take the cut section of the cylinder, if you look at this, the first side of the face is dr, and the next face is rd phi, and the third face is z direction. So by using the first law of thermodynamics only, you will be deriving the heat transfer equations. So now I'll use the whiteboard. Just a second. Okay, sorry for the delay. So we all know that the heat transfer generalized heat equation can be derived with respect to first law of thermodynamics, that is dq is equal to du plus dw, where I will split this equation as q plus u is equal to, I mean dq plus u is equal to u plus du plus dw. So let this heat input is 1 and the internal energy is 2 and the increase in internal energy is 3 and the work done is 4. Like earlier class only I am doing, don't worry. Okay. As we are considering a small cylindrical element, the net work done will be 0. So you can eliminate this. So you all know that the internal energy generated within the system is assumed to be some q dot with respect to its volume. So that is dr, dz, rd phi. So your second term is also achieved. And now the third term is rate of increase of internal energy. It will be depending upon mass into specific heat into change in temperature with respect to time, okay, per unit volume. So it will be dr, dz, rd phi. So this is your third term. So now what about your first term? So total energy generated in or total energy given to the system. Here we are having three directions. What are those? dr, dz and rd phi. Am I right? So we shall find individually the net heat generated, net heat involved in the system, and then we shall add those three so that we can get the net heated in the system. So first we shall take in the r direction. So if you see the earlier slide, okay, I'll draw here. Sorry, I'll write here. We are having three direction. So in the first right side of the from the left side, we are giving some r amount of heat. Okay. But at the exit, so see here, you are giving q of r as input, and at the outlet, you are getting q of r plus dr. So the net heat in the r direction will be q of r minus q of r plus dr. So we all know Q of R is nothing but, according to Fourier's law of conduction, it is minus, sorry, K into, with respect to R direction, KR, AR, dt by, here it is thickness in place, we will take the cylinder radius, dr. So I can write it as minus KR into, what is the area? Surface area will be dz and rd phi. So dz rd phi into dt by dr. So you know what do you mean by QR. Then how to find the Q of R plus dr? In your mathematics, you have seen Fourier series of expansion, that is f of x plus h is equal to f of x plus 1 by 1 factorial of d by dx f of x dx plus 1 by 2 factorial of d by dx d square by dx square f of x whole square dx, like that. So I will be expanding in respect to, I'll considering the only first term, 2 terms, d by dr of q of r into dr, okay, so on. So you know q of r, so I no need to write it. So plus d by dr of, we know that qr is minus kr into dr dz r d phi into dr by dr with respect to dr. Okay, so we are having here r into dr. So if you apply the UV rule, and you will be getting as, on further simplification, you will be getting as Q dash is a Q of R minus Q of R plus delta RS minus KR into dt dz, sorry, dz R d phi dr into dou square T by dou R square plus R into dou T by dou R. And the Z and phi R is constant, so we can take it directly as, after this adding these two, I can get it as 1 by R of dou R by dou R kr into dt by dr plus 1 by R square dou square y by dou x square. So like this. So with respect to your volume, I am taking entire dr dz dphi as constant. I can remove it. Okay. So this is your generalized heat conduction equation in cylindrical coordinates. So next is thermal diffusivity. Thermal diffusivity is nothing but the ratio of thermal heat conductivity to the heat capacity. So which is given as K by rho Cp into P. So it is the ability of the material to conduct the thermal energy to, and also to store the thermal energy. For if there is having larger value of alpha, there will be easily adapting for thermal environment. If the value is low, it is slowly to be and take reach to equilibrium very slowly. Okay. So these are some important questions. Thank you.